Alright, so this is our last model before the exam, and then we're going to switch over into something else, but I wanted to talk about the SIR model, and it's a model for the spread of disease, and you may have heard of this one before, but let's talk about how we're going to construct this model. We're going to be thinking of the population as being divided into three groups. Group 1 is going to be the group of susceptible susceptible individuals. So we'll call that population S of T. 2, infected individuals, I of T. And 3, the R stands for recovered. And so they will be R of T. Okay, and so we're going to assume that anybody in the population can be classified into one of these three things, right? In the real world, it gets more complicated than that, but we'll assume that that's the case for the time being. Okay, so now this is what's going to be called a compartmental model, where we think of our S of T almost like a tank. And so this is going to be like a tank mixing problem. But it's even simpler than our tank mixing problem. So moving from the S tank into the I tank, we'll assume that we have some constant multiple of the S of T that's moving. And then from the I tank into the R tank, we'll assume that we have some constant multiple gamma I. Okay. Now, can we write down our differential equations from that? Actually, before we do that, I want to make some more assumptions just to be sure everything's clear. So what we were saying before is that the population has to be one of these three things, and so therefore some of our model assumptions will be that the population is large and constant. And so that means in our notation, S, in fact, this is going to be true at any time T. If I take S of T plus I of T plus R of T, that's always equal to, that doesn't look like an R. Let me change that to an R. Whoa. My eraser doesn't work all of a sudden. R equals N. Try that one more time. There we go. R of T equals N. Good. So what does that mean? We don't have any births, no deaths. Oops. So there's nothing coming or going out of our population. This is a closed system. No immigration or emigration. No immigration or emigration. Right, and so we can actually bring those kinds of things into play later, but it's good to see what happens when we don't have any of that initially. Because the thing about mathematical modeling, and we're going to try to model that ourselves, is that you always want to start simple, the simplest assumptions possible. Okay, and so what's another simplifying assumption? No latent period. Okay, so when someone moves from susceptible to infected, for example, that's an instantaneous move, right? You're not spending time like half susceptible and half infected, for example. Okay, and similarly from infected to recovered, that's going to happen. At some point you move from infected to recovered. Okay. Some other simplifying assumptions is that we're going to assume homogeneous mixing. What does that mean? Well, we know what it means in terms of the salt in the tank, right? And it's going to be the same thing here, and that is that think of the population as being, the entire population as being well stirred, so that if you take, a sample from any part of the population, it looks generally the same as any other part of the population. Okay. Now, I should say the infection rate, we're also going to assume the infection rate is proportional to the fraction of infected. Okay, which actually means that the lambda that we're using isn't actually a constant. Well, you could think of it, well, lambda itself won't be constant. It'll change in time, but it's going to be equal to proportion of the infected. So that's the fraction of the infected is I over n, right? Because n is the total number of infected. And then we're proportional to the fraction of infected. Okay, good. All right, and so now I think we can write down our equations that define the three things. So what is the rate of change? The rate of change of the susceptibles is going to be minus lambda s of t. And then the rate of change of the infected, right, it's incoming from the susceptible, so that's just lambda s of t, right? But then the infected also has a loss, right? And the loss is, I guess I can bring it back up here. So it's incoming from S and outgoing to R, right? And so that means we have minus gamma times I. Good, and then dr dt is just going to be, the incoming is just going to be the gamma times I. Good. Now, we can change our lambda there, so I'm going to go ahead and write this long ways. The ds over dt is going to be minus beta times I over n times s, and then di over dt is equal to beta I over n times s minus gamma I, and then dr over dt is equal to gamma times I. Good. Now, I don't have to do this. Oh, by the way, what happens when I add these three? So you might just note ds over dt plus di over dt plus dr over dt is equal to what? 0. Therefore, s plus I plus r is equal to a constant, right? And so everything's working out the way it should. And actually, when you see this, if you have s and I defined, right, if you're able to solve for s and I using these top two equations, then the r is actually redundant, right? Because if I know what s and I are, then I can just write that r is equal to n minus s minus I. Right? And so I don't really need all three equations. And so one way you might write that then is just the two equations in two unknowns, right? Now I should say, when we do our numerical simulations, we're going to go ahead and keep all of it. So we're going to keep everything in 3D, but you don't have to. Okay, so then R of t is n minus s of t minus I of t. Good. All right. Now, we have about 45 seconds left for this video. I just wanted to, the next section, we're going to be talking a little bit about the parameters parameters, beta, gamma, and then we're going to also introduce a new parameter, and that's called R sub 0. That's the basic reproductive number. You may have heard a lot of news about this number in the beginning of our pandemic. There was a lot of talk about what this R0 is. Okay, so we'll discuss that in the next video. See you then.